Put your hand on the table in front of you. It feels solid because atoms refuse to pass through atoms. The wood or glass or plastic under your palm has shape because electrons arrange themselves in shells, because quantum rules give ordinary matter its architecture, because the empty space inside every atom is protected by laws that do not care whether you understand them. Now imagine those same laws being dragged into a place where gravity is not a gentle downward pull, but a verdict. Imagine matter squeezed until atoms no longer have room to be atoms, until protons and electrons are forced into each other, until chemistry, minerals, cells, and molecules all become meaningless words. What remains is not a rock, not a metal, not a star in any familiar sense. What remains is a neutron star, an object so dense that a mountain's worth of mass can fit into a spoonful, yet small enough that a city could span it from edge to edge. But the real controversy is not that neutron stars are dense. That part is almost the easy part. The harder question is what nature is actually hiding inside them. We often describe a neutron star as a ball of neutrons, as if the name explains the thing. It does not. That phrase may be one of the most useful lies in astronomy. It gives us a handle, but it also hides the argument. A neutron star is not just a dead stellar core. It is a boundary dispute between gravity, quantum mechanics, and nuclear physics. It is the place where the universe asks whether the particles we know remain themselves under pressures no laboratory can reproduce. The uncomfortable thesis is this: neutron stars may be the most honest objects in the sky because they do not let any theory stay vague. Either matter can survive as nucleons under crushing density, or it changes into something stranger. Either our equations of state are stiff enough to hold up stars heavier than 2 suns, or they fail. Either the core is mostly familiar nuclear matter, or it is a hidden ocean of hyperons, quarks, condensates, and phases of matter we have only named, not confirmed. A cautious physicist will object immediately, and that objection matters. We do not yet have a photograph of a neutron star core. We have no sample of its matter. We cannot drill into one, and we cannot recreate its deepest pressures in a machine on Earth. Some of the most dramatic claims about neutron stars are still model dependent. Hyperons may appear, or they may be suppressed by repulsive interactions. Quark matter may exist, or the transition may never occur inside the stable stars we observe. Nuclear pasta may be real, but its exact shape, strength, and thickness remain uncertain. The strongest version of the counterargument says that neutron stars are not proof of exotic matter at all. They may be extreme, but still largely describable by nuclear physics, stretched carefully beyond the laboratory. That is a serious position. The evidence has not forced one answer, but it has forced the question, and that is where the drama begins. To understand why a neutron star is not merely a collapsed object, we need to begin before the collapse, inside a massive star that is still alive. A star like the Sun will not make a neutron star. Our Sun is powerful by human standards, but quiet by stellar standards. It burns hydrogen into helium in its core, and when its central hydrogen is gone, it will swell, shed its outer layers, and leave behind a white dwarf. Dense, hot, fading, but not catastrophically strange. The Sun does not have enough mass to continue the chain of fusion all the way to iron. It will not build a core heavy enough to crush electrons into protons. Its death will be dramatic for anything nearby. But in the language of the universe, it will be a retirement, not an execution. Massive stars live under harsher laws. A star born with roughly 8 or more times the mass of the Sun carries a different fate from the beginning. More mass means stronger gravity. Stronger gravity means higher pressure in the core, Higher pressure means hotter nuclear burning. And hotter burning does not simply use fuel faster, it uses it extravagantly. A star 20 times the mass of the Sun does not live 20 times longer because it has 20 times more fuel. It lives far shorter because it spends that fuel like a torch in oxygen. Its core burns not with the measured patience of the Sun, but with the violence required to keep the whole star from collapsing under its own weight. That is the first lesson hidden in the life of every neutron star. Its birth is not an accident at the end of a star's life. It is the consequence of an entire lifetime of imbalance. Massive stars are always negotiating with gravity, and gravity is always raising the price. Hydrogen fusion buys time, helium fusion buys less time. Carbon, neon, oxygen, and silicon buy almost no time at all. Each fuel requires a higher temperature. Each stage gives back less useful energy per particle than the one before. Each stage lasts a shorter span. A massive star may burn hydrogen for millions of years, helium for a fraction of that, carbon for perhaps hundreds or thousands of years, depending on its mass, neon for months or about a year, oxygen for months, and silicon for roughly a day. This is not a smooth aging process. It is an acceleration toward failure. Inside such a star, the core eventually becomes layered like an onion, but the image is too peaceful unless we remember what the layers mean. They are not decorative rings. They are emergency engines. Near the surface, hydrogen may still burn in a shell. Deeper down, helium burns into carbon and oxygen. Deeper still, carbon burning creates neon, sodium, and magnesium. Neon and oxygen burning build heavier nuclei. Silicon burning assembles iron group elements. The star is no longer one furnace. It is a set of nested furnaces, each hotter, denser, and more temporary than the last, surrounding a central region that is becoming the one thing a star cannot use as fuel: iron. Iron is not evil in a human sense. It is stable. That stability is exactly the problem. Fusion releases energy only as long as the products are more tightly bound than the ingredients. From hydrogen up toward iron, the star can gain energy by building heavier nuclei. But iron group nuclei sit near the peak of nuclear binding. To fuse iron into heavier elements costs energy instead of releasing it. Iron is not the next log on the fire. It is ash. When enough ash piles up in the center, the star has reached the end of its bargaining power. Gravity still demands support, but fusion has nothing left to offer. Before the final collapse, the iron core does not immediately fall. It is held up by a quantum pressure that has nothing to do with ordinary heat. Electrons obey the Pauli exclusion principle, which says that identical fermions cannot all pile into the same quantum state. As the core is squeezed, electrons are forced into higher and higher momentum states. Their quantum refusal to overlap creates electron degeneracy pressure. This pressure supports white dwarfs, and for a time it supports the iron core of a massive star, but it has a limit. Chandrasekhar showed that beyond roughly 1.4 solar masses, electron degeneracy pressure cannot hold up a stellar core. When the iron core approaches that limit, the support that has been quietly preventing catastrophe becomes insufficient. Then gravity stops negotiating. The collapse of the core happens so quickly that it almost feels insulting to the millions of years that led to it. A structure roughly the size of Earth, already dense beyond ordinary imagination, collapses into an object only around 20 kilometers across. Infall speeds can reach a significant fraction of the speed of light. The pressure rises so violently that iron nuclei are broken apart by high-energy photons, undoing the nuclear construction that the star spent its final stages building. This process, photodisintegration, steals energy from the core at exactly the moment when support is needed most. At the same time, electrons are driven into protons through electron capture, producing neutrons and neutrinos. The electrons that once helped hold the core up vanish into neutrons. The core becomes more neutron-rich, more compact, more desperate. The neutrino burst is one of the least visible and most important parts of the event. To human eyes, a supernova is a flash of light, but the light is only a small side effect of the real energy release. The collapse releases most of its gravitational energy as neutrinos, ghostly particles that barely interact with matter. In an ordinary setting, a neutrino can pass through planets almost as if they were fog. But a collapsing stellar core is not ordinary. It produces such an absurd number of neutrinos that even a tiny fraction of their interactions becomes decisive. Most escape, carrying energy away into space. A small portion deposits energy behind the stalled shock wave. That energy helps revive the shock and drives it outward, blowing the star apart. This is one of the places where caution is necessary. A simple version of the story says the core bounces and the bounce explodes the star. That is incomplete. The bounce launches a shock, but the shock tends to lose energy and stall as it plows through infalling material and breaks apart heavy nuclei. The neutrino heating mechanism is a leading part of the modern explanation for many core collapse supernovae, but the details remain an active field of research. Rotation, magnetic fields, turbulence, convection, asymmetries, and the structure of the progenitor star all matter. The universe does not always explode stars in the neat, one-dimensional way our first explanations preferred. The more carefully we simulate supernovae, the more we see that the explosion is not a single push, but a complex negotiation between gravity, neutrinos, nuclear matter, and fluid instability. If the explosion succeeds, the outer layers of the star are hurled into space. Carbon, oxygen, silicon, sulfur, iron, and heavier elements are scattered into the galaxy. Some of the elements heavier than iron can be made in supernovae, and neutron-star mergers play a major role in producing many of the heaviest elements through rapid neutron capture. The exact cosmic origin of every heavy element is a field of continuing research, but the broad truth is clear. Violent stellar deaths enrich the universe. They turn the products of nuclear burning into the raw material of planets and bodies. The calcium in bones, the iron in blood, the oxygen in air, and the atoms in rock all carry the memory of earlier stars. A neutron star is born from destruction, but the explosion around it is also a form of distribution. The death of one star becomes the chemistry of future worlds. At the center of that wreckage remains the collapsed core. If its mass is low enough, it becomes a white dwarf. If it is too high, it collapses into a black hole. But in the narrow middle, gravity is stopped by a different quantum defense. Neutrons, like electrons, are fermions. They also obey the Pauli exclusion principle. When they are packed together at nuclear densities, they resist further compression. In addition, the strong nuclear force, attractive at certain distances, becomes repulsive when nucleons are pushed too close together. Together, neutron degeneracy pressure and nuclear repulsion can hold up the remnant. Not gently, not comfortably, but enough. That enough is a knife edge. A neutron star is not stable because gravity is weak. It is stable because gravity has been fought to a draw by the quantum nature of matter. The star is roughly the mass of the sun, sometimes more, packed into a sphere no wider than a metropolitan area. Its density is comparable to the density of an atomic nucleus. A sugar cube-sized piece of neutron star matter would weigh about 1 billion tons on Earth, though in reality, such a piece could not simply sit on a table as a neat souvenir. Remove it from the crushing gravity and pressure of the star, and its state would not remain ordinary. The familiar comparison is useful for scale, but the real object is not a portable mineral. It is a global equilibrium. It exists because the entire star holds itself together. The surface gravity is savage. If you approached a neutron star, the difference in gravitational pull between the near side and far side of your body would tear you apart long before you landed. The escape velocity from the surface can be a large fraction of the speed of light. Light itself, climbing away from the star, loses energy to the gravitational field. It is redshifted. The star's gravity bends photon paths so strongly that an observer can see more than half the surface at once. Light from the far side curves around into view. A neutron star is not a black hole, but it is close enough to the edge that space-time is visibly distorted. It is matter standing just outside oblivion. Rotation makes it even stranger. The original star rotated, perhaps slowly. When the core collapses, conservation of angular momentum spins the remnant up, just as a skater spins faster when pulling in their arms. A neutron star may rotate many times per second. Some millisecond pulsars rotate hundreds of times per second, with the fastest known pulsars spinning so rapidly that their equators move at a significant fraction of light speed. The fact that such objects can remain intact is itself a measurement. It tells us the material must be strong enough, the gravity intense enough, and the equation of state supportive enough to keep the star from flying apart. Magnetic fields add another layer of extremity. A typical neutron star can have a magnetic field trillions of times stronger than Earth's. Magnetars push this still further, with fields that may reach 1,000 trillion Gauss or more. In such fields, atoms become distorted. Vacuum itself becomes a nonlinear optical medium. The empty space around a magnetar can behave as if it has a preferred direction for polarized light. When a magnetar's crust shifts and its magnetic field rearranges, it can release enormous flares of X-rays and gamma rays. The star is small, but its magnetic environment can dominate space around it like an invisible machine. And yet, after all those numbers, after all that violence, the deepest question remains simple. What is it made of? The name suggests the answer: neutrons. But if we stop there, we miss the entire point. A neutron star has structure. It has an atmosphere, a crust, an inner crust, a core, and possibly an inner core, where matter changes its identity. Each layer is a separate argument with its own physics. To call the whole object a ball of neutrons is like calling Earth a ball of rock and forgetting the oceans, mantle, liquid outer core, and solid inner core. The simplification is not wrong at first glance, but it is too crude to tell the story. The outermost atmosphere of a neutron star is almost absurdly thin compared with the star beneath it. It may be only centimeters to meters deep, depending on composition and temperature, yet it is what X-ray telescopes see. It can contain hydrogen, helium, carbon, or heavier elements depending on the star's history. Gravity sorts elements ruthlessly. Lighter elements float above heavier ones. In that extreme field, an atmosphere becomes a compressed skin, hotter than any flame, thinner than paint on a cannonball, and informative enough that astronomers can use its X-ray spectrum to infer temperature, gravity, composition, and sometimes radius. Beneath the atmosphere lies the outer crust. Here matter is still recognizable as nuclei and electrons, though only barely. Nuclei form a crystalline lattice immersed in a sea of degenerate electrons. Near the surface, the nuclei may resemble iron group elements, but with increasing depth and pressure, electrons are captured by protons, and nuclei become more neutron-rich. These nuclei would be unstable on Earth. They would decay quickly if removed from the star. But under neutron-star pressure, they are stabilized, locked into a structure that could be among the strongest known materials in nature. The crust is not thick compared with the star, but it matters enormously. It can crack. It can store stress. It can participate in glitches and magnetar flares. It is the hard shell over a quantum engine. The phrase strongest material in the universe is dramatic, and it needs caution. We cannot put neutron-star crust in a testing machine. We infer its strength through nuclear theory, simulations, and astrophysical behavior. But the conclusion is not empty hype. The expected shear strength of neutron-star crust is extraordinary because the lattice is compressed to densities where ordinary chemical bonding is irrelevant. These are not atoms in the way we normally imagine atoms. They are nuclei held in place by electromagnetic forces and dense electron seas under pressures beyond any terrestrial material. A mountain on a neutron star might be only millimeters or centimeters tall. Yet even that tiny imperfection could involve enough mass and stress to radiate gravitational waves if the star spins rapidly enough. As we descend, the pressure continues rising until nuclei can no longer hold all their neutrons. At the neutron drip line, neutrons begin to leak out of nuclei and move through the lattice as a separate fluid. This marks the transition into the inner crust. Now the star contains neutron-rich nuclei, electrons, and free neutrons. Those free neutrons are predicted to form a superfluid. The word sounds delicate, but it describes something profound. A fluid with zero viscosity, flowing without ordinary friction. On Earth, we observe superfluidity in helium at temperatures near absolute zero. In a neutron star, the temperature may be millions of degrees, yet relative to the enormous Fermi energies involved, the neutrons can still pair up and enter a superfluid state. This is one of the most beautiful contradictions in the subject. A neutron star is unimaginably hot by human standards and quantum cold by the standards of its own particles. Temperature alone does not tell the story. What matters is how the thermal energy compares with the energy scales of the system. In neutron star matter, neutrons may form Cooper pairs and move as a collective quantum fluid. The star becomes a place where superfluidity and nuclear density coexist, where something like a laboratory low-temperature phenomenon appears inside a million-degree stellar corpse, because density changes the rules of what cold means. This superfluid is not just an exotic detail. It may explain one of the most revealing behaviors of pulsars: glitches. Pulsars are rotating neutron stars whose beams sweep past Earth with extraordinary regularity. Many are more stable than human clocks over long intervals. Yet some suddenly spin up by a tiny amount, then gradually relax. These glitches are not random noise from instruments. They are physical events inside the star. A leading explanation involves the mismatch between the slowing solid crust and the superfluid interior. The crust loses rotational energy over time through magnetic braking. The superfluid, weakly coupled and rotating through quantized vortices, can lag behind or maintain a different rotation rate. When vortices unpin from the crustal lattice in a sudden avalanche, angular momentum is transferred to the crust. The star spins up. We see a glitch. A glitch is a message from the interior. It is a tiny change in timing reaching Earth after traveling across interstellar space, but encoded inside it is the behavior of matter, at densities we cannot touch. It tells us that the neutron star is not a rigid ball. It has layers moving against each other. It has pinned vortices and internal reservoirs of angular momentum. It has a memory of stress. Each glitch is like a seismic tremor from a world whose crust is nuclear matter and whose oceans are quantum fluids. Deeper still, near the base of the crust, the nuclei may enter one of the strangest predicted phases in astrophysics: nuclear pasta. The names are playful because the shapes resemble spaghetti, lasagna, tubes, and slabs. The physics is not playful. At these densities, the strong nuclear force, which favors clustering nucleons, competes with the electric repulsion among protons and the pressure of surrounding particles. Instead of round nuclei, matter may arrange itself into rods, sheets, tunnels, and connected networks. These structures may be incredibly strong and may affect neutrino transport, thermal conductivity, crust rigidity, magnetic evolution, and gravitational wave emission. Here again, a careful voice matters. Nuclear pasta is strongly predicted by many models, but not directly observed as a layer we can image. It is an inference from nuclear physics and simulations under extreme conditions. Different models produce different details. The thickness of the pasta layer, the exact shapes, the transitions between them, and their mechanical properties remain uncertain. But the idea is not a fantasy. It is a plausible consequence of known forces at densities near the transition from crust to core. If it exists, the most solid thing in the universe may be arranged like a cosmic joke, the hardest material we can imagine named after dinner. Below the crust, nuclei dissolve. The outer core begins. This region makes up much of the star by volume and mass. Here, matter is expected to be a quantum liquid of mostly neutrons, with a smaller fraction of protons, electrons, and possibly muons. The neutrons are likely superfluid. The protons, because they are charged and can also pair, may become superconducting. That means the outer core could simultaneously contain a neutron superfluid and a proton superconductor. These are not decorative labels. They shape the star's magnetic and rotational behavior. In a superconductor, magnetic flux may be confined into quantized tubes. In a superfluid, rotation is carried by quantized vortices. The interaction between vortices and flux tubes may determine how the star spins down, how its magnetic field evolves, and how glitches propagate. At this point, the neutron star becomes a machine made of quantum order. It is not chaos all the way down. It is structured by rules so strict that angular momentum and magnetic flux are divided into discrete threads. Imagine a star more massive than the Sun, spinning several times per second or hundreds of times per second. And inside it are microscopic vortices and flux tubes negotiating how the whole object loses energy. That is not a metaphor for complexity. It is the actual problem. The large-scale behavior of a pulsar may depend on the pinning and motion of quantum defects inside matter denser than an atomic nucleus. Magnetars may be where this internal machinery becomes violent. Their magnetic fields are so powerful that the crust and field are locked in a strained relationship. Magnetic stresses can twist the crust. Crustal fractures can rearrange magnetic fields. A sudden shift can release intense high-energy radiation. Some magnetar flares are powerful enough to disturb Earth's upper atmosphere from across large fractions of the galaxy. These events remind us that a neutron star is not simply cooling in silence. It can store magnetic energy and release it suddenly, like a spring wound inside a city-sized corpse of nuclear matter. Then we reach the inner core, and the honest answer becomes, we do not know. That sentence should not be treated as a weakness. It is the center of the entire story. The inner core of a neutron star may reach several times nuclear saturation density. At those densities, particles are forced into regimes beyond direct experiment. The familiar description of matter as neutrons, protons, electrons, and muons may remain valid, or it may break. New particles may appear. Neutrons may convert into hyperons. Quarks may become deconfined. Meson condensates may form. Matter may enter color superconducting phases, or some combination of these possibilities may occur in ways that are not captured by simple labels. The first candidate in this uncertainty is hyperonic matter. Hyperons are baryons, like protons and neutrons, but they contain strange quarks. In ordinary conditions, they are unstable. They decay quickly. But in a neutron star core, the energy cost of continuing to pack neutrons into higher states may become so high that creating hyperons is energetically favorable. That sounds reasonable. It follows from the same quantum logic that governs the entire star. More particle species mean more ways to distribute energy. The system can lower its total energy by opening new channels. But hyperons create a puzzle. When they appear in many models, they soften the equation of state. A softer equation of state means less pressure at a given density. Less pressure makes it harder to support heavy neutron stars. Observations show neutron stars with masses around 2 solar masses and perhaps higher. Any viable equation of state must support them. If adding hyperons causes the maximum mass to fall below observed masses, the model fails. This is the hyperon puzzle. The particles seem expected, but their consequences seem dangerous. The strongest counter-argument is that the puzzle may not disprove hyperons. It may prove that our calculations of hyperon interactions at high density are incomplete. Repulsive hyperon-nucleon, or hyperon-hyperon interactions, especially many-body forces, could stiffen the matter enough to keep heavy neutron stars stable. But those interactions are difficult to measure. Laboratory data on hypernuclei helps, but it does not fully reproduce neutron star cores. So hyperons remain suspended between plausibility and constraint. They are neither confirmed nor easily dismissed. Another possibility is quark matter. Protons and neutrons are not fundamental. They are made of quarks bound by gluons. Under ordinary conditions, quarks are confined. Try to pull one out, and the energy creates new particles rather than releasing a single free quark. But at very high density, confinement may give way. The distinction between one neutron and the next may dissolve. Quarks could move through the core as a collective phase of matter. This is not the same as the hot quark-gluon plasma created briefly in heavy ion collisions. Neutron star quark matter, if it exists, would be cold dense matter, cold relative to the enormous quantum energies involved. If quark matter appears, it might not be a simple soup. Quarks could pair, producing color superconducting phases. In one theoretically elegant possibility, color-flavor locked matter, quarks of different colors, and flavors pair in a highly symmetric state. Such phases would have transport properties, neutrino emission rates, viscosities, and gravitational wave signatures different from ordinary nuclear matter. But elegant is not the same as confirmed. The inner core may contain quark matter. It may contain only hadronic matter. It may have a sharp phase transition, a smooth crossover, or mixed phases with their own internal geometry. The data has not yet selected a winner. This is the central controversy of neutron star physics. Not whether neutron stars exist, not whether they are dense, not whether they form in core collapse supernova. Those are established. The controversy is whether the core is the last fortress of ordinary nuclear matter, or the first accessible window into a different phase of the strong interaction. The problem matters because the answer would not only describe one kind of star, it would tell us what matter is capable of becoming. It would test quantum chromodynamics in a region no accelerator can directly reach. It would connect the death of massive stars to the earliest moments of the universe, when quarks and gluons moved freely before settling into hadrons. How do we test such a thing from hundreds or thousands of light years away? We cannot cut the star open. We cannot send a probe. The only option is to read the star's signals with enough precision that the core leaves fingerprints. The most important fingerprints are mass, radius, tidal deformability, thermal evolution, spin behavior, gravitational waves, and the aftermath of mergers. A neutron star's radius is not an arbitrary surface measurement. It is a consequence of pressure throughout the interior. A stiffer equation of state produces a larger star at a given mass. A softer one produces a more compact star. Measure the mass and radius well enough, and the interior begins to confess. This is why pulsar timing matters. In binary systems, the regular pulses from a neutron star can be used as a clock. Relativistic effects in the orbit reveal masses with exquisite precision. Heavy pulsars around two solar masses set a hard lower bound on the maximum neutron star mass. Any equation of state that cannot support them is wrong. That single statement has killed many beautiful theories. It is not enough for a core model to be interesting. It must hold up the stars we actually observe. NICER added another tool. Mounted on the International Space Station, it observes X-rays from pulsars and models hotspots on their surfaces. Because strong gravity bends light, we can see more of the surface than Newtonian intuition would allow. The way the X-ray brightness rises and falls as the star rotates depends on mass, radius, hotspot geometry, and space-time curvature. By modeling these pulse profiles, researchers can infer radii. Measurements of pulsars like J0030 and J0740 have begun to narrow the allowed mass-radius relation. The results suggest radii on the order of about 12 to 13 kilometers for typical neutron stars, with uncertainties, and they challenge both extremely soft and extremely stiff models. Here, the careful counterargument returns. Radius inference is hard. It depends on atmospheric models, hotspot shapes, background subtraction, instrument calibration, and assumptions about geometry. Different teams may use different modeling frameworks and obtain overlapping but not identical results. The measurements are powerful, not magical. They do not yet reveal the core directly. They narrow the map. They make some roads less likely. They do not yet tell us which road reaches the center. Then came gravitational waves. On August 17, 2017, detectors observed GW170817, the merger of two neutron stars. The signal did more than confirm that neutron stars spiral together and collide. It measured how the stars distorted each other before the collision. Tidal deformability is a measure of how easily a star is stretched by its companion's gravity. A large, fluffy star deforms more. A compact star deforms less. That deformation leaves an imprint in the gravitational waveform. By reading it, physicists constrained the equation of state. The data disfavored very large, very easily deformed neutron stars and helped push the field toward more compact radii. The electromagnetic counterpart made the event even richer. A short gamma ray burst arrived shortly after the gravitational waves. A kilonova followed, glowing as newly formed heavy elements decayed. The color and time evolution of the light revealed neutron-rich ejecta and helped confirm that neutron-star mergers are major factories for heavy elements. The event linked gravitational waves, gamma rays, optical and infrared light, nuclear physics, and cosmic chemistry. One collision became a laboratory spread across the universe. But GW 170817 also showed how much remains uncertain. The merged object had a mass above what a cold, non-rotating neutron star can likely support. It may have survived briefly as a hypermassive neutron star, supported by rapid rotation and thermal pressure, before collapsing into a black hole. The survival time matters. If it collapsed immediately, the ejecta and light curve would differ. If it lived longer, the remnant could inject additional energy. Different equations of state predict different thresholds and lifetimes. The data gives clues, but not a final verdict. We are learning not from one clean number, but from a tangled aftermath. The next galactic supernova would add another kind of evidence. When a massive star collapses nearby, neutrino detectors would likely see a burst before visible light emerges from the stellar envelope. The supernova early warning system links detectors across the world to alert astronomers to a coming core collapse event in our galaxy. If such an event occurs, the neutrino signal will carry information from the forming neutron star seconds after birth. It would be a rare direct glimpse into the physics of collapse. We have seen supernova neutrinos before from SN 1987A, but modern detectors are vastly more prepared. A nearby event would flood the field with data. This is why neutron stars feel different from black holes. A black hole hides its interior behind an event horizon. A neutron star refuses to hide completely. It is extreme but visible. It pulses. It glitches. It cools. It flares. It bends light but lets light escape. It shakes space-time and mergers. It sends neutrinos during birth. It allows matter to approach the edge of gravitational collapse while remaining, in principle, observable. It is the densest object we can study directly. That makes it more than a corpse. It is a messenger from a region where matter almost stops being matter. Now imagine standing not on the surface because no body could stand there, but in thought, just above it. The star below you is only about 20 kilometers wide, yet it contains more mass than the sun. The horizon around you would look strange, because light from the far side bends upward. The sky would be distorted. If the star is hot, X-rays pour from the surface. If it is a pulsar, magnetic poles beam radiation into space. If it is a magnetar, the magnetic field itself is a landscape of danger. The surface under you is not rock. It is a crust of nuclei and electrons under gravity so intense that a fall of 1 meter would release energies that ordinary explosions cannot imitate. Move downward in imagination. First the atmosphere, a thin bright skin. Then the outer crust, a lattice of exotic nuclei. Then the inner crust, where neutrons drip out and superfluid currents carry angular momentum. Then the pasta layer, if the models are right, where nuclear matter becomes rods and sheets. Then the outer core, a sea of superfluid neutrons and superconducting protons threaded by quantum vortices and magnetic flux tubes. Then the inner core, the place where the map becomes a question mark. This is not a descent through distance. It is a descent through certainty. The deeper we go, the less the words mean what they meant at the surface. There is a temptation in documentary storytelling to treat that uncertainty as permission for exaggeration. The core might contain quarks, so we say it is a quark star. It might contain strange matter, so we say strange matter would infect the universe. It might contain exotic phases, so we call it impossible. But uncertainty is not a blank check. The honest version is stronger. The core may contain exotic matter, but we do not know. Observations allow some models and exclude others. The true drama is not that anyone can claim anything. The true drama is that nature has built an experiment we cannot reproduce, and we are forced to solve it from signals arriving as pulses, spectra, cooling curves, and waves in spacetime. Strange matter deserves special care. Some speculative ideas suggest that at high density, strange quark matter could be more stable than ordinary nuclear matter. In the most extreme versions, if a seed of strange matter touched normal nuclear matter, it might convert it. This idea has often been dramatized into cosmic horror, but it is not an established threat. It depends on uncertain assumptions about the stability of strange quark matter, surface tension, charge, and weak interactions. There is no evidence that neutron stars are spraying dangerous strangelets through the galaxy. There is no reason to turn a theoretical possibility into a panic. The science is interesting enough without pretending the sky is full of contagious quark droplets. The same discipline applies to black hole thresholds. We know neutron stars have a maximum mass, but the precise value remains uncertain. It depends on the equation of state and rotation. A cold, non-rotating star has one limit. A rapidly rotating star can support more mass temporarily. A differentially rotating remnant after a merger can support even more for milliseconds or seconds before collapsing. That means the boundary between neutron star and black hole is not a single simple number for all situations. It is a landscape: mass, spin, temperature, magnetic fields, composition, and time. Still, the principle is unforgiving. Add enough mass, remove enough support, and gravity wins. This raises a philosophical question that is also scientific. Is a neutron star a success or a failure? It is what remains after a star fails to support itself through fusion. But it is also matter's refusal to surrender completely. It is a failed black hole, or perhaps a successful star corpse. It is born from collapse, yet it does not collapse all the way. The universe takes a stellar core, crushes atoms out of existence, and then quantum mechanics says stop. Not forever in every case. Not beyond every mass, but for billions of years in many cases, stop. That stop is profound. The same Pauli exclusion principle that shapes the electrons in atoms and makes chemistry possible also helps hold up the remnants of dead stars. The rule that prevents electrons in your body from all falling into identical states is related in spirit to the rule that keeps neutrons in a neutron star from giving gravity the final word. You and a neutron star are not similar in scale, temperature, density, or violence, but the same quantum grammar underlies both. The universe does not have one set of laws for the kitchen table and another for the collapsed core. It has one set of laws, pushed from gentleness to extremity. That is why neutron stars are such severe teachers. They make comfortable separation impossible. Nuclear physics is not only a subject for laboratories, it determines the radius of a star. Quantum mechanics is not only a subject for microscopic particles, it supports objects more massive than the sun. General relativity is not only a theory of abstract spacetime. It bends the light from a surface and shapes how we measure radius. Particle physics is not only the search for smaller things. It may determine whether the core contains hyperons or quarks. A neutron star is not an object owned by one field. It is where fields collide. Consider the radius problem. A difference of 1 or 2 kilometers may sound small. For a star, it is tiny by ordinary astronomical standards. But for neutron star physics, it is enormous. A 12-kilometer radius and a 14-kilometer radius imply different pressures inside the core. A more compact star suggests softer matter at certain densities. A larger star suggests stiffer matter. When detectors and X-ray instruments narrow that radius, they are not merely measuring a size. They are testing how matter resists compression. They are asking whether dense matter is a stubborn solid like nuclear fluid, a softer mixture with exotic species, or something that changes phase at depth. The mass measurements are equally ruthless. A 2-solar mass neutron star is a verdict against many soft equations of state. It says whatever you put in the core, it must still push back hard enough. That single fact makes the inner core debate difficult. Exotic matter often softens the star. Observed heavy stars demand stiffness. Theories must solve both. They must allow whatever particles or phases are energetically favored without making the star collapse too soon. This is why the most interesting models often involve a softening at some density followed by a stiffening at higher density, or repulsive interaction strong enough to restore support. The star is not asking for imagination alone. It is asking for consistency. There is also the cooling problem. Young neutron stars cool by emitting neutrinos from their interiors and photons from their surfaces. The rate of cooling depends on the particles and processes inside. If certain direct Urca processes occur, neutrino cooling can be rapid. If superfluid gaps suppress reactions, cooling changes. If exotic matter exists, it may open new cooling channels. Observing neutron star temperatures at different ages can therefore constrain the core, but ages are uncertain. Distances are uncertain, atmospheres complicate spectra, and magnetic fields distort heat flow. The signal is real, but it must be interpreted carefully. Accreting neutron stars offer another probe. In binary systems, matter pulled from a companion falls onto the neutron star and releases gravitational energy as X-rays. Sometimes accretion turns on and off. During outbursts, the crust is heated. During quiet periods, it cools. Watching that cooling curve lets astronomers infer thermal conductivity, heat capacity, and crust composition. Some observations suggest that the crust conducts heat very efficiently, and possible pasta layers may affect how heat escapes. Again, the neutron star becomes a laboratory not because we visit it, but because it responds to stress in measurable ways. The idea that the crust can crack brings us back to magnetars. If the magnetic field inside and around a magnetar evolves, it can stress the crust until it fractures. A star quake in a crust only a kilometer or so thick can release more energy than any earthquake by absurd margins. But the quake is not simply a geological event scaled up. It is tied to magnetic reconnection, particle acceleration, and radiation. A magnetar flare is the star telling us that its interior and exterior cannot be separated. The magnetic field is anchored in matter. Matter is strained by the field. When one shifts, the other answers. The core may also reveal itself through gravitational waves in future detections. A rapidly spinning neutron star with a tiny asymmetry could emit continuous gravitational waves. A merger signal can reveal tidal deformability, a post-merger remnant, if detected at high frequencies by future detectors, could carry information about the equation of state with extraordinary detail. The oscillation frequencies of the remnant would depend on mass, radius, thermal pressure, rotation, and composition. In a sense, the star would ring. If we could hear that ring clearly enough, we might identify whether the core underwent a phase transition. We are not there yet, but the possibility is real. A phase transition in the core could produce a dramatic signature. Some models predict twin stars. two neutron stars with the same mass but different radii because one contains a quark core and one does not. Others suggest that a strong first-order phase transition could alter merger dynamics, collapse thresholds, or post-merger gravitational wave spectra. But these remain hypotheses awaiting decisive evidence. They are not inventions for drama. They are legitimate consequences of equations. Still, until observations select them, they must remain conditional. This conditional language does not weaken the story. It strengthens it. A mystery is more powerful when the door is genuinely closed, not when we pretend we already walked through it. The inner core of a neutron star is not a place where we can freely project fantasies. It is constrained by masses, radii, tidal deformabilities, cooling, pulsar timing, nuclear experiments, and theory. The uncertainty is bounded. That is the difference between science and mythology. Science does not say anything is possible. It says these possibilities remain after the evidence has eliminated others. If we compare neutron stars to black holes, the contrast becomes sharper. A black hole simplifies itself from the outside. Mass, spin, and charge largely determine its exterior. It hides complexity behind the horizon. A neutron star displays complexity. It has a surface. It has multipole moments, magnetic fields, hotspots, crustal behavior, oscillation modes, and thermal evolution. It is messier than a black hole, and for that reason, it may be more informative. A black hole is a clean answer to gravitational collapse. A neutron star is a complicated refusal. This refusal has consequences for cosmic history. Neutron stars do not simply sit as silent remnants. They can become pulsars, timing beacons so regular that their pulses reveal planetary companions, binary dynamics, relativistic effects, and gravitational waves from distant supermassive black hole binaries through pulsar timing arrays. They can accrete matter and produce X-ray bursts. They can merge and create colonovae. They can generate gravitational waves. They can forge heavy elements. They can, through their deaths and collisions, contribute to the chemistry of planets. The first confirmed detection of gravitational waves from a binary neutron-star merger changed the field because it combined messengers. Light told one part of the story. Gravitational waves told another. Gamma rays told another. Optical and infrared spectra revealed heavy elements. The event was not only a collision, it was a proof that the universe speaks in multiple languages at once. Neutron stars are among the few objects that force us to become multilingual. Radio for pulsars, X-ray for hot surfaces and accretion, gamma rays for flares and bursts, neutrinos for birth, gravitational waves for mergers. What would it mean if quark matter were confirmed in neutron star cores? It would be one of the deepest discoveries in modern astrophysics. It would show that the universe naturally creates stable macroscopic regions of deconfined dense quark matter. It would connect stellar remnants to the strong force in a way no laboratory can duplicate. It might reveal color superconductivity as not merely a theoretical phase, but a real component of stars. It would tell us that at the heart of a dead star, matter has crossed a boundary back toward a state more fundamental than neutrons. What would it mean if no exotic matter is needed? That would also be profound. It would mean ordinary nucleons, under interactions strong enough and repulsive enough, can support stars up to the observed masses while producing the measured radii. It would show that nuclear matter remains itself farther into compression than many theorists expected. It would be a triumph of nuclear physics, not a disappointment. The absence of exotic matter is not boring if it is forced by data. It would tell us something hard and valuable about the strong force. This is why the best version of the neutron-star controversy does not cheer for one outcome. It asks what nature chose. The universe is under no obligation to provide quark cores because they sound exciting. It is under no obligation to preserve neutrons because they make models simpler. Our preferences do not matter. The star has a radius. It has a mass. It has a cooling rate. It has a merger signature. Somewhere in those facts is the answer, one signal at a time. Our job is not to make the answer dramatic. It already is. Let's return to the physical image one more time. A neutron star is about the size of a city. If it replaced a city on Earth, its mass would not simply crush the region. It would dominate the planet. Its gravity would be catastrophic. Its magnetic field, if magnet or strength, would make normal chemistry impossible nearby. Its surface would be 1,000,000 degrees or more if young. Its crust would be stronger than any familiar solid. Its interior would contain superfluid currents flowing without friction. Its core might contain particles that live nowhere else today in stable form. And all of this could fit inside a circle you can drive across in ordinary life. The scale mismatch is part of the terror. It is not vast like a nebula. It is compact. It hides extremity by being small. The smallness matters because it makes neutron stars deceptively close to black holes. Add mass, and the radius may shrink. The escape velocity rises. The redshift grows. The line between visible matter and hidden horizon comes nearer. A neutron star is a last visible outpost before space-time stops letting signals escape. That is why its maximum mass matters so much. The Tolman-Oppenheimer-Volkoff limit is not just a technical value. It is the mass at which matter's known forms lose the argument. Below it, quantum and nuclear pressure can resist. Above it, no known stable support remains. The star crosses from object to horizon. We do not know the exact TOV limit because we do not know the exact equation of state. Estimates tend to place it somewhere above the heaviest observed neutron stars and below the masses of many stellar black holes, but the precise value is still under investigation. Rotation can raise the effective support temporarily. Thermal pressure in a merger remnant can delay collapse. Magnetic fields may contribute in special circumstances, but cold, non-rotating equilibrium has a maximum. The fact that we are still trying to locate it is not a small gap. It is one of the key open doors in dense matter physics. There is a human irony here. We understand enough to predict that neutron stars exist, to detect them, to time them, to watch them merge, to use them as clocks and laboratories. Yet we do not know the final composition of their hearts. This is not because the science is weak, it is because the object is strong. It pushes matter into a regime where every familiar division becomes unstable. Nuclear physics becomes particle physics. Condensed matter concepts become stellar structure. General relativity becomes an observational correction. The core is not hidden by distance alone. It is hidden by the fact that our categories were built in gentler places. That is why the line between knowledge and humility must remain visible in the account of any serious documentary. We can say a neutron star is born when a massive stellar core collapses and protons and electrons combine into neutrons. We can say it is around city-sized in solar mass. We can say its gravity is extreme and its magnetic fields can be enormous. We can say its crust is likely crystalline and its inner components likely superfluid or superconducting. We can say glitches support the existence of internal superfluid components. We can say gravitational waves constrain tidal deformability. We can say nicer constrains radii. But when we reach the inner core, we should say what science says. The answer is not settled. The unsettled answer is not an empty space. It is a battlefield of models. Some equations of state are too soft. They cannot hold two solar mass stars. Some are too stiff. They make stars too large or too deformable compared with GW 170817 and radius measurements. Some include hyperons and must solve the hyperon puzzle. Some include quarks and must match both mass and tidal data. Some attempt unified descriptions from crust to core. Some rely on effective field theory at lower densities and perturbative quantum chromodynamics at very high densities, with uncertain interpolation between. The correct equation of state must pass through all these constraints without breaking. It must be flexible enough for reality and rigid enough for data. There is one more subtle point. The measurements we need are not independent islands. They correct each other. A radius measured by X-rays becomes stronger when combined with a mass measured by radio timing. A tidal deformability measured by gravitational waves becomes more meaningful when compared with nuclear experiments and heavy pulsar masses. A cooling curve becomes more informative when we know the age and distance of the remnant. This is why modern neutron-star physics is called multi-messenger, not as a fashionable phrase, but because no single messenger is sufficient. Light, radio pulses, X-rays, gamma rays, neutrinos, and gravitational waves each see a different part of the same hidden machine. Put them together, and the star becomes less able to lie. That is also why the next decades matter. The first neutron-star merger was not the final chapter. It was the first clear page. Future detectors will hear more mergers, closer mergers, and perhaps the high-frequency ringing after merger where the equation of state speaks most directly. Better X-ray timing will reduce radius uncertainties. Radio surveys will find new massive pulsars or show us where the mass distribution ends. If a pulsar heavier than about 2.5 solar masses is found and confirmed, many current models would be forced into crisis. If none appear despite large surveys, that absence will also carry information. In this field, even silence becomes a constraint. Future observations will tighten the trap. More neutron-star mergers will improve tidal measurements. A nearby supernova would provide neutrinos and possibly gravitational waves from birth. Better X-ray timing will refine mass radius estimates. Continuous gravitational wave searches may detect mountains or internal asymmetries. Radio timing will find heavier pulsars or confirm none exist above a certain mass. Laboratory experiments on neutron-rich nuclei, heavy ion collisions, and nuclear symmetry energy will sharpen the low-density side of the equation. Piece by piece, the inner core will have less room to hide, and perhaps one day the evidence will force a sentence that is now only conditional. Perhaps we will be able to say, the cores of massive neutron stars contain deconfined quark matter, or the core remains hadronic up to the highest stable masses, or a strong phase transition creates twin star branches, or hyperons exist but are stabilized by repulsive interactions, or something stranger, something that does not fit our current classifications. The great value of neutron stars is that they can surprise us without leaving the domain of measurable science. They do not require magic. They require better instruments. There is a final way to understand what a neutron star represents. Ordinary matter is mostly empty space. Atoms have tiny nuclei surrounded by electron clouds. The solidity of your hand, the table, the walls, and the world is a quantum structure, not a miniature pile of billiard balls. A neutron star is what happens when gravity removes that comfortable emptiness. It takes the architecture of atoms and collapses it until the distinction between one nucleus and the next is gone. It takes the exclusion principle that quietly shapes chemistry and turns it into a dam against gravitational catastrophe. It takes the strong force from the scale of nuclei and makes it a pillar holding up a star. It takes the smallest rules and forces them to carry the largest burden matter can bear before disappearing into a black hole. That is the real fear and the real beauty. A neutron star is not merely a place where matter is crushed, it is a place where matter answers. Gravity asks, can you withstand this? Electrons answer for a while, then fail. Neutrons answer next. Nuclear repulsion joins them. Superfluid vortices, superconducting protons, pasta phases, hyperons, quarks, or whatever lies deeper, all become part of the response. The star is not silent. It pulses its answer across space. So when we say a teaspoon of neutron star material would weigh 1 billion tons, we are only touching the surface of the idea. The deeper truth is stranger. That material is not just heavy. It is a different way for matter to be organized. It is matter after chemistry, matter after atoms. Matter under gravity so severe that identity itself becomes negotiable. A neutron star asks whether a neutron stays a neutron when the pressure rises high enough. It asks whether protons and electrons survive as minor components, whether strange particles appear, whether quarks leave their prisons, whether the deepest core is a nuclear sea or a quark ocean. It asks questions our laboratories cannot yet answer. And because it asks them in the sky, we can listen. The fact that we can listen at all is a historical accident made possible by a misread signal. The first pulsars did not announce themselves as collapsed stars. They arrived as pulses so regular that the discovery team briefly gave the source a joking label associated with little green men. That reaction was not foolish. It was a measure of how strange the signal was. A natural object was behaving like a clock, not a rough clock, not a flickering flame, a rotating beacon with a period that could be measured with extraordinary precision. The eventual explanation, a spinning neutron star with beams sweeping through space, was in some ways more astonishing than aliens. Nature had built a lighthouse from a collapsed stellar core. That discovery changed the status of neutron stars from theoretical remnants to observable machines. Before pulsars, neutron stars were a prediction, an outcome allowed by physics after the work of Baud, Zwicky, Oppenheimer, Volkoff, and others. After pulsars, they became astrophysical objects with measurable spin, magnetic field, age, and environment. The pulses were not only proof of existence, they were tools. A pulse arriving early or late can reveal orbital motion. A gradual spin down can reveal magnetic braking. A sudden glitch can reveal internal superfluid dynamics. A pulse profile can help constrain radius. The star that was once invisible became one of the most precise instruments in the galaxy. Supernova 1987A added another kind of confirmation. When a star exploded in the Large Magellanic Cloud, detectors on Earth registered a small burst of neutrinos before the visible light became famous. Only a few dozen neutrinos were detected, but those few were enough. They were the faint trace of an enormous flood, exactly the kind of signal expected from core collapse. For the first time, the hidden birth process of a compact remnant had touched our detectors directly. Light showed the expanding debris. Neutrinos confirmed the collapse physics. The event did not answer every question about neutron stars, and the central remnant remained difficult to identify for decades, but it gave astrophysics something priceless, evidence that the invisible neutrino engine was real. This matters for the controversy because it separates the established scaffold from the unresolved interior. we should not pretend the entire subject is speculation. The existence of neutron stars, their formation in core collapse, their pulsar nature, their compactness, their enormous magnetic fields, and their role in mergers are supported by multiple lines of evidence. The uncertainty begins when we ask for the exact behavior of matter at the highest densities. That distinction is important. A weak documentary turns mystery into fog. A strong one keeps the floor visible while pointing to the cliff beyond it. Even the name neutron-star carries history inside it. It was chosen because neutrons dominate the simple picture, and because the collapse literally creates neutrons by forcing electrons and protons together. But the name can make the object sound finished, as if the discovery of neutrons solved the star. In reality, it opened the problem. Neutrons are not elementary, they are composite. They contain quarks. They interact through forces that become difficult to calculate in many-body dense matter. The star named after neutrons may be the place where the neutron itself stops being the right unit of description. That irony is the intellectual engine of the subject. There is also an observational trap in the popular image of neutron star matter. We often imagine the star as uniformly dense from surface to center, but its density changes enormously with depth. The outer layers are fantastically dense by Earth standards and still thin compared with the inner core. The crust may contain nuclei. The core contains fluid. The central density depends on the star's mass and equation of state. A lighter neutron star may never reach the conditions required for the most exotic phases. A heavier one may cross several thresholds. So there may be no single answer to the question of what is inside a neutron star. The answer may depend on which neutron star we ask. That possibility changes the narrative. We are not looking for one universal interior like a diagram in a textbook. We may be looking for a family of interiors. A young hot neutron star differs from an old cold pulsar. A magnetar differs from a recycled millisecond pulsar spun up by accretion. A low-mass neutron star differs from a heavy one near the maximum mass. A merger remnant differs from a calm, isolated star because it is hot, rapidly rotating, differentially rotating, and violently deformed. The phrase neutron star covers all of them, but nature may hide different matter in different members of the family. This is why future catalogs matter more than any single famous object. One heavy pulsar constrains the maximum mass, but a population of heavy pulsars can reveal whether there is a cutoff. One radius measurement is valuable, but a pattern of radii across different masses can expose a phase transition. One merger constrains tidal deformability, but many mergers across different masses can map how deformability changes. If two stars of similar mass show unexpectedly different radii, that would be a clue. If post-merger gravitational wave frequencies show patterns inconsistent with purely hadronic matter, that would be a clue. The core will not surrender in one sentence. It will be cornered statistically. The deepest irony is that neutron stars are both too small and too massive for ordinary astronomy. They are tiny dots, even to powerful telescopes, yet their gravity reshapes light. We do not resolve their surfaces the way we resolve planets. We infer them through timing, spectra, waveforms, and relativistic modeling. That means every measurement is partly a physical measurement and partly an argument about models. This does not make the science unreliable. It makes it demanding. The data must be squeezed carefully, and the assumptions must be declared. A radius without a model is not a radius. A pulse profile without a space-time calculation is not enough. A gravitational waveform without tidal modeling cannot speak fully. This is where the debate becomes healthy instead of sensational. Competing teams may disagree about uncertainties, priors, atmosphere composition, waveform systematics, or nuclear theory inputs. That disagreement is not a scandal. It is the machinery by which the answer becomes harder to fool. The star is extreme enough. We do not need to invent conspiracy or certainty. We need better constraints. We need disagreement that improves the model rather than noise that replaces evidence. In a field where 1 kilometer of radius can matter, humility is not decoration. It is calibration. The ordinary observer might ask why any of this matters if neutron stars are distant and unreachable. The answer is that neutron stars test the same matter from which everything is made. They test the strong force, the behavior of dense fermions, the limits of quantum pressure, the coupling between matter and space-time, and the origin of heavy elements. They are not separate from us. The atoms in our bodies exist because earlier stars forged and scattered elements. The principles that support neutron stars also structure ordinary atoms. The gravitational waves from neutron star mergers have already taught us where some heavy elements are made. When we study neutron stars, we are not studying an alien exception to physics. We are studying our own physics under interrogation. The question is not whether a human can survive near such an object. No human can. The question is whether our ideas can survive near it. Can our nuclear models survive 2 solar mass pulsars? Can our quark models survive radius constraints? Can our superfluid models survive glitch statistics? Can our merger simulations survive the next gravitational wave catalog? Can our understanding of magnetism survive magnetar flares? Every neutron star is dangerous, not to our bodies, but to our confidence. It forces theory to prove that it can carry weight. Somewhere in our galaxy, a pulsar is spinning, with a rhythm so exact that an error in its arrival time can reveal a hidden planet or a gravitational disturbance. Somewhere else, a magnetar is storing magnetic stress in a crust stronger than steel by unimaginable factors. Somewhere, an old neutron star is cooling, its X-ray glow carrying clues about its interior heat capacity. Somewhere, 2 neutron stars are orbiting each other, losing energy to gravitational waves, slowly falling toward a merger that will shake space-time and forge heavy elements. Somewhere, a massive star is building an iron core that will collapse and create a new neutron star in a burst of neutrinos. The universe is full of these laboratories, but they do not announce themselves in human language. They speak in pulses, spectra, flares, glitches, waves, and neutrinos. We are learning the grammar. Every detection improves it. Every contradiction matters. A pulsar too massive for a model kills the model. A radius too small or too large trims the possibilities. A merger waveform tightens the equation of state. A cooling curve hints at superfluid gaps. A glitch reveals angular momentum hidden below the crust. It is slow detective work, but the suspect is the nature of matter itself. That is why neutron stars deserve a more serious kind of awe than simple shock. They are not impressive because the numbers are large, though the numbers are almost absurd. They are impressive because they make the universe testable at its extremes. They take the invisible rules behind everyday existence and push them until they almost fail. They show us that solidity, identity, pressure, magnetism, rotation, and even the meaning of matter are not fixed intuitions. They are consequences of deeper laws. Change the density, and the familiar world disappears. The counter-argument remains. Perhaps we should not overstate the mystery. We know a great deal. We know neutron stars form from massive stellar cores. We know they can pulse and accrete and merge. We know their masses can be measured. We know their radii are being constrained. We know nuclear theory provides a workable framework for large parts of the star. It would be wrong to present neutron stars as pure unknowns. They are not. They are among the most studied compact objects in astronomy. The controversy is not a fog that erases knowledge. It is a sharp frontier at the center of knowledge. That frontier is exactly what makes the story worth telling. If everything were already known, a neutron star would be a monument. Instead, it is an experiment still running. It has been running since the moment the parent star collapsed. It will keep running as the star spins down, cools, glitches, accretes, flares, or merges. A neutron star is a long-duration physics experiment designed by gravity and powered by collapse. We are late-arriving observers reading its output. One day, perhaps, the phrase neutron star will feel misleading in a new way. Perhaps we will discover that many heavy neutron stars are hybrid stars with quark cores under nuclear mantles. Perhaps we will reserve the word neutron for the outer core and use new names for the inner region. Perhaps we will find that the stiff nuclear interactions prevent most exotic phases from appearing in stable stars. Perhaps the answer will vary with mass. Lighter stars, mostly nucleonic, heavier stars with phase transitions. That possibility is especially appealing because it turns neutron stars into a sequence of hidden interiors. The same class of object could contain different kinds of matter depending on mass and history. If so, the heaviest neutron stars become the most valuable. They push deepest into the density frontier. They are where hyperons, quarks, or condensates are most likely to appear if they appear at all. But they are also closest to collapse. They live nearest the edge. A heavy neutron star is not just a massive pulsar. It is a question pressed almost to breaking. Its existence says the equation of state must be stiff enough. Its radius says how stiff. Its cooling says what particles carry energy. Its glitches say how superfluid components couple. Its merger behavior says how matter fails under extreme tides. Everything about it is evidence. There is a strange comfort in that. The universe has places we cannot visit, but not all inaccessible places are silent. The inner core of a neutron star is inaccessible in the practical sense. No craft could survive the approach. No sample can be returned. No human eye can see through the crust. Yet the core influences the whole star, and the whole star influences the signals we detect. The center speaks through the surface. The invisible becomes measurable through consequences. That is science at its best, not direct possession, but disciplined inference. At the end of the journey, imagine the neutron star not as a monster, but as a compressed library. Not a library of words, but of physical regimes. On its surface, radiation under savage gravity. In its crust, exotic nuclei in a lattice stronger than anything Earth can build. Below that, superfluid neutrons slipping through crystalline structures. Near the base, possible nuclear pasta, geometry at nuclear scale. In the core, quantum liquids, superconducting protons, muons, and perhaps particles or phases that mark the boundary between known matter and something deeper. Every layer is a page. Every pulse is a signal that the book is still being written. And the book began with death. A massive star ran out of usable fuel. Its iron core exceeded the limit. Electrons were forced into protons. Neutrinos escaped. A shock wave tore the star apart. The galaxy received new elements, and in the center, where total collapse might have made a black hole, matter found one last form of resistance. That resistance became a neutron star, a city-sized object with solar mass, a rotating, magnetic, relativistic, quantum nuclear remnant. A thing too extreme for ordinary intuition and too observable to ignore. The next time you hear the phrase dead star, be careful. A neutron star is dead only if life means fusion. It is not dead as a physical system. It is active, structured, evolving, and communicative. It may pulse for millions of years. It may flare. It may accrete. It may merge. It may one day collapse. It may hold in its center the answer to what matter becomes when squeezed beyond atoms, beyond nuclei, perhaps beyond neutrons themselves. It is less a corpse than a locked chamber, still vibrating from the force that created it. And the lock is beginning to turn. More gravitational wave detections will come. More radius measurements will come. More massive pulsars may be found. Better models will sharpen the equation of state. Nuclear experiments will constrain the symmetry, energy, and interactions of neutron-rich matter. Future detectors may hear post-merger oscillations. A nearby supernova may one day flood our detectors with neutrinos and give us the birth cry of a neutron star in real time. When that happens, the frontier will move. The inner core will remain difficult, but less hidden than before. Until then, the honest ending is not certainty. It is vigilance. The neutron star tells us what we know, what we suspect, and what we have not yet earned the right to say. It is a warning against easy conclusions. It is also an invitation. The universe has placed a laboratory in the sky where matter is pushed to the edge of collapse, but not beyond it. We cannot enter it, but we can read it. We cannot touch it, but we can measure how it trembles. We cannot see its core, but we can force our theories to answer for it. The deepest objects often teach us by refusing to be simple. A neutron star is simple only from far away, a point of light, a pulse, a catalog entry. Up close, it becomes a layered argument. Every kilometer inward changes the physics. Every new observation changes the allowed interior. That is why the story is not finished. So the real question is not simply what is inside a neutron star. The real question is whether matter, under enough pressure, remains loyal to the identities we gave it. Does a neutron remain a neutron? Does a core become strange? Do quarks break free? Does the star hide a phase transition strong enough to change its radius, its merger, its sound? We do not know yet. But the sky is already sending the data. Somewhere, a pulsar ticks. Somewhere, a magnetar strains. Somewhere, two neutron stars spiral inward. Somewhere, the next signal has already begun its journey toward us. And when it arrives, it will not only tell us about a dead star, it will tell us whether the matter that makes everything, including us, has another face waiting in the dark.